Right, okay, linked lists. Um, Flexible structure. We often draw it graphically. Um, Oops, done something. Oh, hang on a minute, I'm pressing the mouse button. Oh, jeez. I just caught the mouse button. Right, okay, so we draw them graphically like this. So we have a pointer called a head that points to an object that contains the data that we're trying to store in the linked list, but also a link to another item. Okay, so another object. So it's just a load of connected objects, connected by pointers. So we don't know where in memory these are. They come from the heap. They dynamically allocated memory. So which is the same place where any new object in object-oriented programming comes from. But we can, and this we would call a dynamic linked list. So this is dynamic because we don't know, or we don't have to request how much memory we need to store this before we start. But we can allow it to grow and shrink on the demands of the application, whatever the application is. Okay, it's got certain issues. Its main issue is you can only follow it linear. So a linear processing system, which is not a problem if you need to process things in a linear way. So, always from the first item and processing to the end. But if you need to add and remove items, that's quick, but you have to do a linear search. Okay, so in its raw sense, a standard one-dimensional linked list is quick for removing and deleting. In fact, it's super quick if you want to add a new item at the start, because all you've got to do is replace the head pointer. So we go, where's the head pointing? Let's point to that. And then we go, well, make the head point to that. So insertion at the head is the quickest operation. Okay. To delete something, you have to search for it. So you get this linear processing again. Okay. So if the order doesn't matter and we just want to insert at the head all the time, then that's fine. If you only ever want to process the end of the list, then you could have a end pointer, but the problem you would then have is, how do you update it if I delete this one? You wouldn't know what was pointing to it. It's a little bit like, if you think about it, it's how hyperlinks work on a web page. A web page doesn't know what's linking to it, but multiple things can link to the same web page. Okay, so that's your dynamic linked list. So searching is a linear process, which unfortunately means deleting is a linear process, because you've got to search first for the item that you want to remove, which has to be linear. If you want to insert to keep something alphabetical or numerically ordered, again you'd have to search. There is no way of using binary search with a standard linked list, because you don't know where the middle is. Okay, right, so we can, instead of using the heap and this dynamic allocation, we can do a statically allocated linked list. So a static linked list. And we do that by providing an array. And this is why it's static, because we use an array. Now, the exam board would say that this array is just a 2D array, but you could argue it is a 2D array. This is what it looks like in a really wonky way. Remember, most of the questions in the exam will be like this. Okay, where you've got your array location. So that's the index. That's not very good. Hang on. Index. And then for the standard linked list, we have got our data and we have got our link. So this is mimicking the same structure that we've got in our object. We've got data and then a link, but we just represent it using an array. Now, in reality, this should be an array of records. Where the record is of this format. So we might have record, and we call it a linked list. And then inside there you would have your data item. And then you would have your link item. And you can have arrays of records. So in the same way that we could do this as a class. Okay, and then all we do is we'd need to decide if we were going to use the static method. We'd need to decide before we run our program, so at design stage, how many elements we'd want maximum. And then we'd create an array of that size. So in this NAFO example, I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 10 items I can store in this linked list. Now looking back at the dynamic one, because the don't worry about all that scroll up there, I was zooming around. I'll just pretend it wasn't there. Because the allocation is coming from the heap, we don't worry about where that memory comes from and where free space is, because that's the heap's decision to make. We just ask. You always put the keyword new. So you're like new player or something like this. When you're creating an instance of a class, you doing that, you're saying, oh, give me some space from the heap. We don't know where that comes from or how it's decided what that is. But when we're doing a static linked list, we've got to manage the empty space. So this is the complication of using the static linked list. It's efficient memory wise because we allocate before. Okay, we statically allocate the space. So we have a head pointer which keeps track of the start of the linked list, but we also need a free list pointer. So we have to manage where all the free space is. So let's assume that this linked list is currently empty. Okay, so I'm gonna put in a load of links, just sequential links here. -1, remember, we use as null, so it indicates no link. And it makes sense when we're doing array references to use -1 for null, because it's an illegal, don't talk about Python, it's an illegal index reference. So we could trap it and check for it really easily. You wouldn't use 0, obviously. Right, so the free list would point to the first element in our static link that is free. So the head in this case would point to null, to say there is no items in the list. So essentially what we've got to do is we've got 2 linked lists. So in order to implement a static linked list, you actually have to manage 2 linked lists. The one that's got the data in that head points to, and the one that's got all the free space that free list points to. Okay, so if we were asked to add, let's just say we're doing I don't know, fruit. They seem to like fruit and colours. I'll do fruit. I've got to think of some fruit now. I want to add the following items. So I'm going to have orange, avocado, which I can't spell, so I shouldn't pick that. Avocado, I don't know, something like that. A lime, another fruit. Can't think of another fruit. Hang on a minute. What is some of these? Avocado. Have I spelled it wrong? Pineapple. That's a good one, Tilly. Pineapple. It's a bit long though, isn't it? Pineapple. Yeah. A what? Richard, you're being stupid. A kiwi fruit, that's nice and short. Yeah, they do. I have seen that on the exam. Right, that'll do, that'll do. I don't want any more. Right, so I'm just going to add them. So the process, and you might have to do this in a question. The process first is to find the free list. So we look at the free list and we go, oh, that space is free. So we're gonna just do them in the order I've written them down. So I'm going to put orange in the data item bit. Obviously, the data item is going to be a bit bigger than this, and in general, it isn't going to be a single item. It's probably going to be a pointer to some bigger object. So a list of information that's associated, and the data might actually be a key, a unique item. Right, so I do that. So now I can say, right, oh, I've got the head currently points to -1, so I want to update the head pointer. So I've got to be careful in the order that I do this. The free list needs to be updated, so it points to the next item. So before I overwrite this link, I must say, right, okay. And again, just like when we do the Dijkstra and the A star, don't scribble things out. Show the exam board that you've updated a pointer. So I'm going to take what the following link from that free one was. So that now I'm saying 1 is where the next free space is. And because we've done it linear, they are going to be in order like that. Now, the head currently points at -1, but I'm going to, because I don't care about the order, I'm inserting at the head. So what I'm going to do is I'm going to overwrite where the head points as the link that's going to follow orange. So orange is going at the front of the list. So it needs to point to what was previously the head of the list. So I'm going to overwrite that and I'm going to put -1. I don't care that it's -1. I'm just saying it's the current head pointer. Okay, once I've done that link, I can then update the head and say, well, the head is at position 0. Okay, so that's added that first thing. Well, let's have a go at putting avocado in. So we look at the free list. The free list says, oh, there's space at position 1. So I'm going to put avocado. Spelt wrong, I don't care. Right, so I need to update the free list first. So I need to say, right, what was following position 1? Oh, that was 2. So let's update the free list with 2. Right, we want to insert avocado at the head. Okay, so the head currently points to 0. So what we need to do is update the link for avocado to point to whatever the head pointing to. Then we can update the head to point to our new item, which is at position 1. Okay, so we carry on going through this process. I'm going to add lime. So same thing again. Lime, update the free pointer. And then I'll show you how you delete one in a sec. Update the free pointer. Update lime's pointer to point to the head so that it's inserted at the start. And then update the head to point to the new start of the list. So if we just stop and have a look. So following the head pointer, I'm just going to scroll that across a bit. Looking at the head pointer, position 2, we go lime. Following lime is at position 1, which is avocado. Following avocado is 0, which is orange, and then there is nothing, so that's the end of the list. Okay, so let's just put pineapple in. So again, look at the free list. That's where we've been allocated space. The free list management is easy because we don't care about the order of the free list. So it's always looking at the head all the time. So there's no search involved to process the free list, which is quite nice. Right, so I'm going to say, right, following that first item in the free list was 4, so that's what we're going to update the free list to. And then we're going to look at head. Head is currently pointing at 2, so I'm going to update pineapple and make its link the same as the head pointer. Then I'm going to update the head pointer to be 3. Last one to put in kiwi, so that's at position 4. So update the free list with whatever position 4 points to next, which is 5. Look at the head pointer. That's pointing at 3. So we want kiwi to be at the start of the list. So we're going to overwrite kiwi's pointer with 3. And that's why we had to do it in that order. Otherwise, we'd have lost the free list. and then we're going to point the head to where Kiwi is. Okay, so I've got 5 items in my list. I don't know how many items are in the list unless I do a linear count, starting at the head and run through until I get to the null pointer. In the same way that I don't know how many items I've got in the free list either. I'd have to do the same thing. I could start at 5 and go like follow 6, 7, 8, 9. Oh, there's the end of the list. 5 spaces. So if you was going to implement this system in reality, what you would probably do is you keep track of how many items you've got in there. So every time you add something or insert something, you'd increase the counter by 1 and you decrease the free counter by 1. Every time you remove something, you alter those counters again. So you keep track of these things rather than saying, oh, I can save 1 variable space by running through the list all the time, which would be slow. You'd only do that in extreme memory systems, like maybe if you've got a watch, or even though watches have got lots of memory these days, but hey, cheaper watch. Right, okay, let's say we want to delete or remove from the list lime. Okay, so the problem we've got is serial search, so we can only go from the head. So we look at 4 and we go, oh no, that's Kiwi, that's not what we want. Let's move on to the next thing. So we look at 3, oh, that's pineapple. Let's move on to the next thing. 2, that's the one we want. So this is the one we want to delete. Okay, we've just put a marker on that. The problem we've got when we do this is that we mustn't forget where we just came from. Because to delete this, we've got to jump. We've got to just skip over. We want to update pineapple's pointer so it points to lime's pointer. So we want that to go there. So when you do this, there's 2 ways. You can do it using recursion, or you can do it just using a loop, but you need to keep track of the previous list item index that you was on. Okay, so assuming I did that and I know where I previously were, I can say I can delete lime by saying, oh, it points to 1, so let's update pineapple with that pointer value, and we put a 1 in there. Now, so you can see that the list now goes kiwi to pineapple to avocado to orange. So it's been deleted, but we need to add that back to the free list. So again, what we do is we insert at the head of the free list. So we look at free list and we say, oh, that currently is pointing at 5. So we update our lime and we say, right, well, actually, lime needs to point to 5, and then the free list can point to lime. So that becomes 2. And that's the process. So if we just check to make sure that the free list worked, so we go to 2, so where lime was, that will get overwritten next time. That then points to 5, which points to 6, 7, 8, 9, and then that's the end. 9 is the last one. If we look at the head pointer, just to check that's working, we've got 4, which is kiwi, which says look at 3 for the next one, which is pineapple, which says look at 1 for the next one, which is avocado, which says look at 0, which is the next one, and then orange says, oh, that's the end of the list. Okay, so it's a process, and it is about making sure you do things in the right order. Now people would say, why would you use a static linked list? Well, because we've got more flexible control. We are not doing heap allocation. This comes from a different area of memory. Okay, so when the compiler builds our program, it can look at this definition for this size of this array that we want, and it can allocate from the static memory allocation and just adds it to the pool that an application gets. So instead of it coming from the heap, it's from this static area, so where all the global variables are stored as well. But it's complicated. There is a lot of steps involved, whereas with this, the static one, we haven't really got that many steps. Okay, because all the free stuff is being handled by another process. Now, if I was building this, which I have built these lots of times, what would be a good thing would be to have the free list as a separate process. So you make requests to the free list. So you make an abstract interface. So someone says, return, deallocate an item at this location, or please give me the location of an item. And you would have you know, in a object oriented program, you would have probably a free list manager that would give you, so you make your own little allocator, and it wouldn't matter to the program that was generating the linked list how that memory is being allocated. All it needs to know is there's a location where a record can be stored, because you could theoretically have lots of linked lists all from one big block of static allocated array, and you use a free list manager to process those and let the thing that's messing about with the linked list do its own. You could have multiples of them, and that'd be quite good. Okay, so it's all about these pointers. It's the same thing for trees. There isn't any tree stuff on the test, but it's the same thing. If you're going to do a tree structure so that you can get benefits of binary search with a linked list, then you just have a left and right pointer. But it's the same setup, really. Just instead of one link, you have two links. You have it, and we'll call them left and right, so that you can mimic this structure. If you're doing a tree structure, you just do it like this. You just have your data, and then you have your right pointer and your left pointer. So if you can do that in a static way, which they have done on the exams as well, you've just got to be careful on how you organize the linked list. They tend to make a table that basically looks like that. So they'll have index, and then it's up to them how they organize it, but they sometimes put the left pointer, the data, and the right pointer in that order to make it easier for you, or they might mess about with it to make it harder for you. So you just get something like that, and that would -1 would indicate there is nothing following. So the left pointer might point to 0, and that might still point to nothing. So you can spot a leaf node. So where we've got 2 pointers to null, they indicate a leaf node. So you can see that really easily. But we have to be aware of that, and that may come up. Right, okay, so that was the linked list run through. Like I say, I'm recording this, so I will upload it. Are there any other topics that any of you lot want me to run through? I'll have a bash at anything. Doing it off the top of my head, I don't mind. Remember, you've got to know both types of queues, the buffer version and the circular version, and the algorithms for both of those. I'm not going to go through those because I've gone through them before, and that's for you to make sure that you look up. If not, I will end this here. I've got a lesson tomorrow with the other class, so I'll do this again, and I'll pick a different thing to go through. I might go through some Little Man Computer stuff, and I'll upload that as well, and I'll just do a few basic Little Man Computer problems, like doing a loop, counting or something. We'll just build that up from Little Man. Okay. Right, I'll leave the meeting open, but I'm going to go dark. And if you want to pop a question, and I'll. Oh, what's that? Yes, Richard, very good. Yeah, so I'm going to turn my camera and mic off. Okay, and I will. I've got you again. Let me just look at my timetable. I've had to print it out. Hang on. I've got you again on Thursday. So the test, I think we've got the test on. Got the test. Is it on Monday? I can't remember what day it is. Anyone know what day the test is? I haven't written it yet. I've still got it to write. Tuesday, right? Okay. Yeah, assuming we're all in next week. Well, let's see what Boris says, because he was talking a bit nonsense yesterday and this morning. In fact, really flabbergasted this morning. But hey, you're lucky, Luke, if you got 3. Yeah, Dara, I do wonder if we're going to get told we're all shut. I I hope at least yous lot are coming in. I wouldn't mind if we just had the sixth form open, to be honest. I mean, it's most of my teaching, but it'd probably be for the best for yous lot. I think the GCSE lot are screwed, to be honest. They've been so messed about. Lucky, elaborate. Your brain's going to be at full flow by the time you get to that last one. It's going to be like so engorged on endorphins. You're going to be like a demon. What you got last? Is it mine? Last? Oh, but every time a thing pops up, it covers up the conversation. Ah, right. Well, you should be rocking by the time you get to computing. It's all going to feed into this aggregated rank thing, which I'm assuming we're going to be using of some description. I think you're still going to get your exams, but I think they're going to get us to rank. It will be functioning by the end of Tuesday. Yeah, this is all a bit stupid. I think what I might do on Thursday, I won't do it with the other class because there's too many people. I was going to say another word, but I called them people in the end. But I might let you turn your microphones off. My brain's never functioning, Richard. This is just like a simulacrum of a human being. I don't know how I get up in the morning, to be honest, half the time. Nothing but a nightmare this morning. But there you go. Yeah, so we'll have a go with the microphones on. Oops. Oh, I've just kicked me £200 desoldering station over. Hang on. I knew I was going to kick that over. Not £200 in weight, £200 in money. Yeah, so on Thursday, I think we'll have a go with the microphones and we can actually try and have a conversation, but the lag is terrible on this. So we'll see how we go with that one. Right, okay, I'm going to sign off. You crack on, keep working on this stuff. It is important, everyone. We'll talk about projects next time I see you. I just hope we've got a little bit more information about what's happening with the exams by the time I see you, which whenever that's going to be. Are you supposed to just come in for exams? I don't even know how that's going to work.